Hi and good day everybody. We are Group 5 and this is our project for MEC682 Solar Energy. So this is our team members. We have Haziq, Asraf, Danish, Izaan and Firdaus. Shown on this poster, our project focus on the design of a rooftop solar PV system located at Gurdwara Sahib Jelapang in Perak. The purpose of this project is to evaluate the technical performance, financial viability and environmental benefits of implementing a grid-connected solar PV system using the feed-in tariff FIT framework in Malaysia. And the purpose also, the purpose system has a total installed capacity of 144 kilowatt using 325 monocrystalline panels and optimized for the available rooftop area. We will also consider factors like solar irradiation, system losses, shading in our energy yield estimation. So with that, I will now pass it over to the next presenter to explain the system design and the performance in more detail.
For the solar photovoltaic system at Gurdwara Sahib Jelapang, our team has carefully designed a high efficient configuration to match the building energy needs and physical constraints. A total of 325 monocrystalline solar panels, each rated at 458 watts, giving us a total installed capacity of 148.85 kilowatts. These are split between roof A with 197 modules and roof B with 128 modules. The roof layout was assessed for sun exposure, shading from nearby tree and structure, and roof angle. Roof A being larger and less obstruct accommodate a majority of the modules. Roof B still contribute significantly, maximize available space without compromise performance. So all the space have been utilized. The module arrangement follow a portrait orientation with uniform string distribution, which improve maintenance, access and ensure consistent thermal ventilation, which is crucial for panel longevity. We select this configuration after running simulation in PVCs, which allow us to test various orientation, string sizes and inverter pairing to minimize mismatch losses and maximize energy yield over the year. So lastly, cable rows were optimized to reduce DC losses and inverter placement was chosen to ensure safety, accessibility and minimal power drop. Both inverter and protection units are placed close to load center, lowering installation and operational costs. This design ensures not just efficiency but reliability and scalability. It will allow the Gurdwara Sahib to reduce electricity costs, meet sustainability goals and operate a low maintenance, long life renewable energy system. That's all from me. Thank you.
Okay, for solar panel selection, we choose brand JA Solar model JM54 D40 450 LB. So the power output of this panel solar selection is 450 watt P and cell technology monocrystalline. Efficiency we take 20.7% for this panel. Dimension is 1762 over 1134 and panel area around 2 meter square. The weight of this panel is 23.5 and temperature range negative 40 degree until 85 degree Celsius. Product warranty 12 year and performance warranty 25 year. Certificate IC 61215. So that's for our solar panel selection. For inverter selection, we choose model Huawei, model Sun 2000 15 KTL. Rate AC output around 15,000 watt. Maximum DC input is 22,500 watt. Max input voltage around 1,100 volt and MPPT operating voltage range 200 until 1,000 volt. So that's my inverter selection specification.
Hello and good day everyone. My name is Firdaus and I will be presenting the main result of our solar PV system simulation using the PVC's application. So as shown here, the system is expected to generate 214.25 megawatt hour per year with a specific production of 1,488 kilowatt hour per kilowatt peak per year. This result reflect the total clean energy output based on the site condition at Gurdwara Sahib Jelapang. On the left, we have a monthly breakdown of normalized production per install (KWP). The red bar show the actual energy injected into the grid, while the small color layer above indicate minor system loss like inverter and PV array collection loss. Okay, next, this table break down the system monthly performance in more detail. We observe key parameters like global horizontal and incident irradiation, ambient temperature, and energy generation at each stage, starting from the PV array to final energy exported to the grid. So overall, the system perform well. Even the monsoon month with good consistency between energy received and injected to the grid. The year-end total confirm a high efficiency and reliable operation with a steady performance ratio. Now let's break down the total system losses. Starting from 1824 kWh per meter square of horizontal irradiation, we experience a 3.4% loss from the angle of the panel and 3.3% IAM loss due to incident angle effect. So PV losses include 0.7% due to irradiance level, 8% from temperature impact, 2% due to module mismatch, and after that 1% of MEC wiring loss, and 1.7% inverter efficiency loss. Okay, this scatter plot shows the daily correlation between solar irradiation and system output. The diagonal alignment shows a strong linear relationship as incident solar radiation increase, so the system output. This confirms that our system is well sized and respond effectively to daily solar availability. So this histogram shows the distribution of system output power through the year. The peak usage lies between 60 to 100 kW, with the rate occurrence of full capacity around 120 kW. This indicates that the system is efficiently used and rarely underperform maximizing without frequent overloading.
Hi, I'm Haziq, and just now my friend Firdaus presented the result using PVCs. And right now I will explain the simulation that we conducted using by PV Watt, which is a reliable tool for preliminary solar yield estimation. So basically, the system parameters were based on our actual design with a DC capacity of 146 kilowatt, fixed till 15 degree and azimuth angle of 180 facing south, with an average solar irradiation of 5.07 kilowatt hour per meter square per day, and accounting for 15% of total system losses. The system is expected to produce around 195,000 kilowatt hour per year. So monthly output varies slightly throughout the year but remains stable, so it indicating consistent solar potential at the site. So these PV watts result help validate our energy prediction and support the feasibility of the proposed design. So the PVCs is a detailed software for designing solar system. It shows things like shading, losses, and how well the system works. It's good for engineer, but PV Watt and the PV Watt is easier to use because it gives a quick estimate of how much energy of a solar system can produce. It's good for the beginner or early planning. So PVCs is for detailed design, professional. PV Watt is for a quick estimate. And now we move to the economic financial analysis of our proposed solar PV system. So the total capital expenditure CapEx estimated at 585,000 ringgit, and the largest cost goes to the solar panels, totaling about 263,000 for 325 units of 450 watts modules. Other major costs include the inverter system, 8 of 15 kilowatts at 64,000, and components such as mounting structure, cabling and BOS, and installation and labor, each ranging around between 58 to 70,000 ringgit. And we also allocated RM 23,000 for the design and permit, and added a contingency reserve of 46,000 to cover unforeseen expenses. So that's the breakdown of the upfront cost of the system. So next, my friends.
Hello, good morning, good afternoon and good night whenever you see this video, sir. I will be presenting the financial analysis section of our solar PV system project, especially from detailed cash flow modeling to the life cycle cost evaluation and sensitivity analysis. Is the cash flow analysis. This system's financial performance was modeled over 25 years. Initial investment is 585,000 ringgit and the revenue remained constant under a fixed feed-in tariff scheme. The O&M cost increased by 2% annually due to the inflation. From the cash flow table, we can see that the system break even in year 9, after which it generates net positive in return. Next, we move on to the payback profitability. This graph illustrates how the cumulative cash flow evolves over the time. The system begins generating surplus cash from year 10 onward, reaching over 1.1 million in profit by year 25. This is the financial indicator. The key financial metrics confirm the system's economic viability. With an NPV of nearly 300,000 ringgit in Malaysia and an IRR of 11%, the project is financially sound. A 9-year payback period ensure we get 16 years of profit after recovering our costs. Next is the life cycle cost evaluation. Over 25 years, the system will generate nearly 1.9 million in revenue. After deducting capitals and O&M costs, the net lifetime profit stands at over 1.13 million. Next is the sensitivity analysis. We also tested financial sensitivity. Even under less favorable conditions like lower feed-in tariff or higher capex, the project maintains a positive NPV and an IRR above the discount rate. This shows a good sign, good resilience to the future uncertainties. To conclude, the project demonstrates a solid financial feasibility with a strong return, manageable risk, and long-term benefit. These findings support the implementation of rooftop solar PV as a viable investment for clean energy. That's all from me. Thank you.
So now we go to the sustainability discussion part.
The impact and carbon saving of our proposed solar PV system at Gurdwara Sahib Jelapang. The system has a capacity of 144 kW and is estimated to generate around 214 and 25 MW of electricity per year. Based on PVC simulation data, using Malaysia grade emission factor of 0.584 kg CO2 per kWh. So to put into perspective, each year this system is equivalent to removing 27 gasoline powered cars from the road, planting over 5,000 trees or avoiding the burning of nearly 50,000 litres of diesel. Looking long term over its expected 25 years lifespan, the system is projected to offset more than 300,000 tons of CO2. So it is improve the energy security of the facility and lead to substantial saving on electric bills. Overall, this project delivers strong environmental and financial returns, supporting both sustainability goals and operational efficiency. UN Sustainable Development Goals. Starting with SDG 13, climate action, the system reduced around 125 tons of CO2 and reducing over 3,100 tons in 25 years, supporting Malaysia carbon goals. For SDG 7, affordable and clean energy is delivered reliable and renewable electricity using high efficiency JA solar panel and grower inverters, improving energy security and cutting costs. It also advanced SDG 11, sustainable cities, by strengthening the energy reliance at a community's religious site. Under SDG 12, responsible consumption, the system uses recyclable material like aluminium and glass with JA solar recovery process, reclaiming up to 92% of panel mass. And lastly, it supports SDG 9, innovation and infrastructure, by demonstrating scalable clean energy technology for other public institutions. Overall, this project delivers long-term environmental, economic and social benefits. And this is the main risk and the uncertainties that could impact our solar PV system real-world performance. Firstly, solar resource variability like changing weather or monsoon patterns can affect energy yield. Although our design reduces shading, future obstruction or panel soiling may still cause unexpected losses. Equipment degradation is also inevitable even with high-quality JA solar panel and Huawei inverters. Performance may decline over time. On the economic side, tariff or policy change such as adjustment to NEM can affect the system payback period. Other risks include installation issues like structural challenge or delays, and maintenance uncertainties such as technician availability or spare parts shortage. Finally, PVCs result
based on assumption, which may differ from real site condition. That's why ongoing monitoring and risk management are essential to maintain optimal system performance and long-term returns.
In summary, solar energy is a smart, sustainable solution for the future. With tools like PVCs and PV watts, we can accurately design and estimate the performance of solar system to match your needs and the budget. So our team use professional software and technical expertise to ensure your system is both efficient and cost effective. So if you are looking for a reliable and experienced partner for your solar project, choose us. Let us help you turn sunlight into saving. See ya.